The night sky has always whispered questions into the human mind. We look up at the stars and wonder, where does it all end? For centuries, astronomy has expanded our view of the cosmos from a flat Earth surrounded by a firmament to a solar system orbiting the sun. Two galaxies scattered across billions of light years. And yet with every discovery, a deeper mystery follows. Today, modern cosmology confronts perhaps the most profound question of all. Is our universe unique, or could it be just one bubble in a vast, unseen multiverse? 8. This idea, the possibility that infinite other realities exist alongside our own ones, belong to the realm of philosophy and science fiction. But in the last few decades, serious scientific theories in cosmology, quantum mechanics and string theory have begun to suggest that a multiverse might not just be fantasy. It could be a legitimate frontier of physics. To understand how we got here, we need to start with the Big Bang. The prevailing theory is that our universe began as an unimaginably hot, dense singularity. Then around 380,000 years later, as the universe began to cool, light could finally stream through the cosmos unimpeded. This moment is known as recombination. Since then, the universe has continued to expand and cool, and matter has begun to coalesce into stars and galaxies. But here's the thing. As far back as we can see, the universe appears remarkably homogeneous, the same everywhere. And not only that, the fundamental structures and constants of physics are also the same. On Earth, the force of gravity is always pulling us toward the ground, not pushing us away. A meter in length on Earth is the same as a meter on any other planet or star. Time is always flowing in only one direction. The various forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces, always behave in the same way. At first glance, this might not seem remarkable. After all, we're only observing what's happening within our own solar system. But scientists have found that this uniformity holds true throughout the entire universe, no matter how far they look. That raises a pretty profound question. Why is the universe so remarkably the same everywhere? And more specifically, why does it appear to have started out exactly the same, just after recombination? Well, one explanation is that our universe is just a tiny sample of a much bigger whole. Imagine standing in the middle of a gigantic field, looking out over a patchwork quilt of many differently colored patches. If you only had the ability to see a small part of the overall pattern, say just a single square foot, you would conclude that your universe was made up of only one type of material. You wouldn't know that beyond the bounds of what you could see. There were countless other squares, each made of a different cloth. In this analogy, the different patches represent different universes. And instead of seeing the edge of the field, we see the edge of our universe. In other words, what we observe as the beginning of our universe might actually be just one patch among many, each with its own set of physical laws and constants. But taken together, they form a grander, vaster whole, a multiverse. That may sound like a stretch, but a similar concept is already well established in physics. Physicists have long since realized that our three-dimensional space is almost certainly embedded in a higher-dimensional reality. That's because string theory and other models of quantum gravity require at least 7 dimensions of space. But if those extra dimensions exist, where are they? Well, according to most physicists, they're curled up and hidden at incredibly small scales. So while we experience the universe as three-dimensional, the reality is that it's really many-dimensional. We just can't see most of those dimensions. If that's possible, then why not the same for space-time? According to some physicists, our universe might be just one bubble in a many-layered structure. One patch of reality among many? In this view, our universe isn't special. It's just one particular selection from a grander whole. So is there any evidence for this? Well, there's one observation that has led many physicists to take the multiverse hypothesis seriously. In 1992, 2 independent teams of astronomers were studying the cosmic microwave background, the afterglow of the Big Bang, when they noticed something strange. Looking at the patterns of radiation left over from the formation of the universe, they saw that on the largest possible scales, the universe appeared to be flat. Now, there are actually 2 possible interpretations of this. One is that our universe is infinite. The other is that it's finite but unbounded. Imagine standing on a flat road. If you walk in any direction, you never encounter an edge. Such a road could extend indefinitely, or it could be circular, with the ends of the road actually joining together. From the perspective of a single traveler, there would be no way to tell the difference. Similarly, on the largest scales, our universe could either be infinite or finite, but without any edges. In other words, the observation that our universe appears flat doesn't actually prove that it's infinite. But in the absence of any other evidence, most physicists have simply assumed that it is infinite. However, some have taken this apparent flatness as evidence that our universe is just one bubble in a larger multiverse. After all, if our universe is curved on the largest scales, if we were to extrapolate outward forever, we would eventually come back to where we started, suggesting that there are no true edges to the universe and therefore no boundaries between other potential multiversal bubbles. In the end, whether or not this apparent flatness is evidence of a multiverse is still an open question. But one thing seems clear: the idea that we might be living in a multiverse is no longer the stuff of science fiction. It's a genuine area of research. Indeed, over the last few decades, the multiverse has become one of the hottest topics in cosmology. For better or worse, the search for a multiverse has captured the public imagination. In movies like Spider-Man, No Way Home, and TV shows like Rick and Morty, the multiverse has gone from a fringe idea to a cultural touchstone. But how should we think about this cultural obsession? Are these stories reflecting a real aspect of the universe? Or are they simply escapist fantasies? Only time will tell. Now, watch. How do we know the universe is expanding? Or check out, why is there something rather than nothing? Is there more than one universe? Before we can even ask that question, we need to define what we mean by the universe. In everyday language, we often use the word universe to describe everything that exists. But in scientific terms, the universe is usually defined more narrowly. It's the observable cosmos, the region of space and time we can access through light and other signals since the Big Bang. The observable universe spans about 93 billion light-years across, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. To us, that scale feels infinite. But it isn't. It's limited by a horizon, the cosmic speed limit set by the speed of light and the finite age of the universe. Anything beyond about 13.8 billion years of light travel time remains hidden from us, forever beyond our view. Now here's the key point. Just because we can see beyond the observable horizon doesn't mean there is nothing there. Cosmology suggests that the universe extends far, far beyond what we can observe, perhaps infinitely so. This leads to two crucial ideas: the observable universe versus the entire universe. What we see is just a fraction. If space continues beyond our horizon, then there could be regions that look very different, or even follow different cosmic histories, the laws of physics at the edges. The Big Bang wasn't an explosion into space, it was the rapid expansion of space itself. If inflation theory is correct, then space may have expanded unevenly, creating isolated pocket universes separated from one another by distances we can never cross. This is where the notion of the multiverse begins. It isn't pulled from fantasy, but from real physics extensions of the same theories that describe the early universe and the formation of galaxies. So, when scientists speak of the multiverse, they're not necessarily imagining parallel Earths with alternate versions of you. Instead, they're asking whether our observable cosmos is just one region within a much larger, possibly infinite reality, where different universes might follow different laws of physics, different constants of nature, and even different dimensions of space and time. From here, the question shifts. What specific scientific ideas lead to the multiverse hypothesis? To answer that, we need to explore the key theories and phenomena that shape this concept, from inflationary cosmology to the strange probabilities of quantum mechanics. The idea that the universe might extend beyond what we can see isn't new. It traces back to ancient Greek philosophers who wondered if their world was just a small part of something much vaster. In modern times, the notion became firmly rooted in physics during the mid-20th century, thanks to two breakthroughs. Einstein's general relativity, published in 1915, showed that space and time, intertwined in a flexible fabric, could warp and curve under the influence of mass and energy. Then in 1948, George Gamow, Ralph Alpher, and others proposed that the universe began with a hot, dense state and has been expanding ever since. They dubbed it the Big Bang Theory. These theories didn't immediately suggest a multiverse. Instead, they reshaped our view of the universe, revealing its dynamic nature and hinting at a grand scale far beyond human experience. By the late 1960s, scientists were accumulating evidence for the Big Bang, the cosmic microwave background, a faint echo of the universe's fiery youth. It's discovered in 1964. By 1992, when NASA's Hubble Space Telescope peered into the depths of space, it confirmed the universe was indeed expanding, bringing the Big Bang closer to acceptance as the dominant model. Yet these developments raised more questions than they answered. What caused the rapid expansion in the first place? How did galaxies form out of an initially uniform haze of matter? And how do we explain the slight temperature variations in the cosmic microwave background? Enter inflationary cosmology. First proposed in the 1970s. This extension of the Big Bang theory posits a period of extremely rapid expansion in the universe, ES, first fractions of a second. Alan Guth, a physicist at MIT, was one of the first to champion this idea. He suggested that a field known as the inflaton permeated the early universe. As it rolled down a sort of cosmic energy hill, releasing its potential energy, the universe expanded exponentially, growing by a factor of 1 followed by 26 zeros in just a fleeting instant. This solves several cosmological problems. The initial conditions required for the Big Bang are resolved by the inflaton field. The universe docent need to be perfectly uniform, since the exponential expansion would have smoothed out any irregularities. And the slight temperature variations in the cosmic microwave background can be explained as quantum fluctuations of the inflaton field amplified during inflation. Inflationary cosmology also naturally leads to the multiverse hypothesis. Here's why. The very process that smooths out the universe, the exponential expansion, can affect different regions in different ways. Eternal inflation proposes that some regions expand faster than others, leading to a kind of cellular structure where different cells expand independently and at different rates. This raises a profound question. If these inflating regions are causally disconnected, do they evolve according to the same physical laws? In other words, is our universe unique, or just one of many? The possibility of multiple universes arises because the inflaton field isn't subject to the same constraints as the matter around us. Its behavior is governed by quantum mechanics. Here's where things get really intriguing. Quantum mechanics introduces a level of randomness into the behavior of subatomic particles. Consider a coin toss. In the realm of quantum mechanics, a coin could be in a state of being both heads and tails at the same time. When we observe the result, say heads, we collapse the wave function, and the particle settles into a definite state. This is the famous some people say quote. The collapse of the wave function seems to be a random event, which means the outcome of a quantum event is only determined once it's actually observed. This apparent randomness has led to interpretations of quantum mechanics that assign probabilities to outcomes. For example, if our coin is in a superposition of heads and tails, we might assign a 50% probability to each outcome. Now let's replace the coin with the inflaton field. Suppose that every time this field makes a quantum jump, it chooses a different law of physics or a different constant of nature. In some universes, gravity might be stronger or weaker. In others, the forces that bind atomic nuclei could be different, leading to exotic forms of matter. This is where the multiverse idea takes flight. Our universe, with its particular laws and constants, might be just one of many. Others have vastly different properties, perhaps entirely hospitable to life or devoid of it. The implications are staggering. If truly random, quantum events govern the behavior of the inflaton field, and any possible configuration of laws and constants has an equal chance of occurring in different inflating regions. This suggests that the universe as a whole is a kind of ensemble, a collection of individual universes, each with its own laws, constants, and history. The challenge now is to make this idea more precise. How can we quantify the probabilities of different inflating regions? How can we link the behavior of the inflaton field to the properties of matter? And can we devise experiments that might offer indirect evidence of other universes? In recent years, physicists have made significant progress in these areas. New mathematical tools from the fields of information theory and black hole physics have allowed them to assign probabilities to different inflationary bubble universes, The holographic principle, which relates the amount of information in a system to the area of its boundary, has played a pivotal role in these calculations. It suggests that the volume of a region of space doesn't matter for determining probabilities.
Only
The boundary does. This implies that all possible universes can be thought of as existing on a lower dimensional surface. The eternal inflation picture thus emerges as just one realization among many of the basic constituents of the multiverse. Other approaches come from string theory and loop quantum gravity. Both attempt to unify gravity with the other fundamental forces of nature, and both introduce extra dimensions. String theory requires a minimum of 10 dimensions, while loop quantum gravity needs at least 4. In both cases, the additional dimensions are not observable because they are too small. However, the mathematics of these theories suggests that they can be extended to include other universes. Let's consider string theory for a moment. Its extra dimensions are typically visualized as curled up into tiny, tightly wound loops. But what if these loops aren't all the same size or shape? What if some are much larger or vibrate at different frequencies? This can lead to the emergence of other universes with different properties. Similarly, in loop quantum gravity, the additional dimensions can be thought of as interconnected nodes and links. By changing the connectivity of these nodes and links, one can arrive at different universes with different geometries. These ideas are highly speculative, but they illustrate the power of theoretical physics to generate multiverse scenarios without relying solely on the randomness of quantum mechanics. So where does this leave us? We began by asking if there are other universes and found ourselves immersed in a rich tapestry of ideas from cosmology to quantum mechanics and string theory. We saw that the multiverse hypothesis emerges naturally from extensions of our current theories, particularly inflationary cosmology and string theory. These theories suggest that the universe as we know it is just one realization among many, each with its own laws, constants, and history. While direct evidence for the multiverse remains elusive, its underlying logic has profound implications. It challenges our intuitive notion of reality, suggesting that what we observe might not be all there is. But it also pushes the boundaries of human curiosity and the quest for understanding. Whether or not the multiverse turns out to be real, the journey to explore its implications will undoubtedly lead to new discoveries and a deeper appreciation of the cosmos we call home. The idea of a multiverse where our universe is just one of many is intriguing. But how did it start? How did we go from the Big Bang to a potential infinite array of alternate universes? As it turns out, the multiverse didn't begin as a figment of science fiction or a product of imagination. It started as a serious attempt to address real scientific problems. In this video, we want to highlight that aspect, the trail of logic that led scientists down the path of exploring a multiverse. So let's follow that trail. Join me as we uncover the scientific journey that gave rise to the multiverse. Stage 1. The puzzle of the Big Bang. For most of the 20th century, Big Bang theory was the leading explanation for the origin of our universe. It posits that approximately 13.8 billion years ago, space and time expanded rapidly from a hot, dense state. Over billions of years, this expansion cooled, giving rise to galaxies, stars, and eventually life. However, by the 1970s, cosmologists began noticing inconsistencies with this model. These weren't simple oversights. They were fundamental challenges that hinted at the limitations of the prevailing understanding of the cosmos. First, the horizon problem. Observations showed that the universe appears remarkably uniform no matter where we look. Galaxies seem evenly distributed in the cosmic microwave background. The leftover radiation from the Big Bang is almost the same temperature in every direction. But regions of space that are so far apart, they could never have exchanged information or energy since the beginning of time. How could they be so similar? This puzzle suggested that there had to be a process that had somehow synchronized the universe, making it more homogeneous than the Big Bang model alone could explain. Next, the flatness problem. The shape of the universe appeared to be almost perfectly flat, balanced between collapsing under gravity and expanding indefinitely. This was surprising because the early universe, based on the Big Bang model, should have had a curved geometry. The fact that it wasn't flat implied some kind of fine-tuning, a remarkable coincidence of values that made it possible for life in planets like Earth to exist. Otherwise, the universe would have either collapsed or expanded too quickly, making life impossible. Then, the monopole problem. Particle physics predicted the existence of exotic magnetic objects. It's called magnetic monopoles that could have been produced in large quantities in the early universe. However, despite extensive searches, none had ever been found. This implied that something was amiss with our understanding of the very early universe. These weren't mere academic questions. They represented cracks in the foundation of our knowledge about the cosmos. Solving them was essential to create a more accurate and complete picture of the universe. Stage 2. Inflation theory. In 1981, physicist Alan Guth at MIT proposed a groundbreaking solution: cosmic inflation. His idea suggested that in the first fraction of a second after the Big Bang, the universe went through a period of exponential expansion, much faster than the speed of light. During this brief instant, space stretched exponentially, solving the major issues plaguing the Big Bang theory. How did it do this? First, inflation stretched space so rapidly that regions which appear very distant today were once close neighbors, providing a mechanism for the universe to become more uniform. Second, it shaped the geometry of space towards flatness, explaining why it's suitable for life. Third, it diluted unwanted relics like magnetic monopoles to such an extent that they became undetectable, resolving the monopole problem. But inflation had a fascinating side effect. The rapid expansion didn't happen everywhere at the same time. In some areas, it ended abruptly, allowing normal matter to condense and forming the universe we know. In others, it continued indefinitely, creating a new universe with its own physical laws and constants, completely separate from our own. This concept introduced a revolutionary idea. Our universe might not be alone. There could be other universes, possibly with different physical laws, existing alongside ours. This naturally leads us to a series of questions. How do these other universes come into existence? Is there a process that keeps generating new ones? And if so, how many universes are there? The answers to these questions lie in the next stage of our journey. Stage 3. Eternal inflation and the landscape. The idea of inflation itself didn't posit an infinite number of universes. It suggested a single instance of rapid expansion followed by the formation of our universe. However, when combined with quantum mechanics, inflation took on a more dramatic turn. Let's delve into this concept through the lens of a thought experiment. Imagine a pot of boiling water. At the molecular level, some molecules move fast, some slow, following a bell-shaped distribution. Now, according to classical physics, once a fast molecule reaches the edge of the pot, it stays outside. But quantum mechanics introduces a twist. Due to the uncertainty principle, there is a small chance that a fast molecule will suddenly reappear inside the pot, even if it started outside. Applying this to inflation, we can think of the molecules as patches of spacetime. Those outside the pot represent regions where inflation has stopped, forming actual universes. And those inside represent regions where inflation continues. But thanks to quantum effects, there's a non-zero chance that a region outside the pot can spontaneously recollapse back inside, restarting inflation. This has two significant implications. First, eternal inflation means that new bubble universes continue to form even now, constantly branching out from our own. Second, the process is random. Each bubble universe has a different set of physical constants and laws, governed by the particular configuration of the inflating patch. This randomness opened up the possibility of an almost incomprehensibly vast number of alternate universes, each with its own unique set of laws. We're talking about a potential 10 raised to the power of 500 or more alternate universes. This concept is known as the string landscape. Each bubble universe or pocket universe is like a separate story unfolding with its own characters and plot twists. Some might be more hospitable to life, while others could have radically different laws of nature. Think about it. On a fundamental level, the properties of our universe, the strength of gravity, the charge of an electron, the mass of a proton, all these properties could be different in other bubble universes. What's more, these differences wouldn't just be in other universes. They'd also be in our past, creating alternative histories for our universe. Some might have supernovas that never occurred, altering the chemical composition of their galaxies. Others might have stars that burn brighter or die younger, changing the course of evolution. Even our planet could be different. With slightly altered conditions, Earth might not have been suitable for life, leaving it unoccupied or inhabited by vastly different creatures. This isn't just a playground for science fiction. It's a serious scientific hypothesis backed by some physicists. And here's the fascinating part. While the multiverse concept might seem far-fetched, it didn't emerge from a desire to create fantastical scenarios. It arose from attempts to solve genuine scientific problems, addressing issues that the Big Bang Theory couldn't resolve on its own. Stage 4. The unification of ideas. The concept of a multiverse really started taking shape around the same time inflation theory was gaining traction. Thanks to the discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson. This radiation is the leftover glow of the Big Bang, stretching back to the earliest moments of the universe. Detailed studies by satellites like COBE, WMAP, and Planck revealed tiny temperature fluctuations in this cosmic microwave background. These ripples represent variations in the early density of matter that evolved into the galaxies and clusters we see today. Remarkably, these fluctuations match predictions made by inflationary models. This convergence of observation and prediction was a pivotal moment, lending strong support to the idea of inflation. If inflation is correct, the multiverse naturally follows. Some regions of space inflate, becoming separate universes, while others continue expanding, creating a vast array of alternate realities. However, this isn't the only source feeding into the idea of a multiverse. Around the same time, string theory was posing its own set of challenges and possibilities. Stage 5. String theory in the landscape. String theory, which emerged in the late 20th century, offers a potential framework to unify all forces of nature, including gravity. At its core, it proposes that the fundamental constituents of reality are unparticles but tiny vibrating strings existing in higher dimensional space. While string theory is mathematically elegant, it presents its own set of challenges and complexities. One of the most significant is the string landscape. This refers to the vast number of possible universes that could exist based on the different ways these strings can vibrate. In fact, string theory allows for an astronomical number of possible universes. It's potentially 10 raised to the power of 500 or more. Each of these universes could have different physical constants and laws due to the unique vibrational states of strings in each. Now, string theory doesn't inherently propose an infinite number of universes. That comes from the combination of string theory's inherent flexibility with the unpredictable nature of quantum mechanics. Think of it like this. String theory provides the basic rules of the game, while quantum mechanics introduces the element of chance. This combination leads to a scenario where new bubble universes continuously branch off from our own, each with its own set of physical parameters and laws. Stage 6. The birth of a scientific idea. As we entered the 21st century, these various ideas came together to form a serious scientific discussion of the multiverse. Inflation suggested bubble universes, quantum mechanics suggested branching universes, and string theory suggested a vast landscape of possible universes. None of these theories were invented to create a multiverse. They emerged from attempts to solve real scientific problems. The multiverse was a consequence and unavoidable possibility that arose naturally from the mathematics. At this point, the idea of multiple universes shifted from speculative philosophy to a legitimate, though controversial, area of scientific inquiry. So there you have it. The idea of the multiverse didn't originate from a desire to fabricate fantastical concepts. It came from a series of scientific inquiries aimed at solving genuine problems in cosmology. The concept of the multiverse emerged as a natural consequence of applying established scientific principles and observations to our understanding of the universe. Whether or not the multiverse actually exists is a different question, one that remains a topic of ongoing research and debate. But what's undeniable is the scientific journey that led to its conception. A testament to human curiosity and the relentless pursuit of understanding the vast cosmos we inhabit. What do you think? Does the idea of a multiverse make sense to you? Or are there aspects that leave you skeptical? Let's discuss. If someone told you that our universe wasn't actually all there is, that beyond the edge of what we can observe lie other universes, their realities, other use, you'd probably think they're crazy. Yet this isn't the stuff of science fiction. It's a serious idea being explored by some of the world's leading scientists. It's called the multiverse. In this episode, we'll look at 7 of the biggest mysteries surrounding this hotly debated topic. Welcome to our channel, where we bring you the latest news and discoveries from the frontiers of science. Join with us as we uncover the secrets of the natural world and beyond. Number 7. Can universes collide? You've seen the movies. When universes collide, the result is explosive. But the multiverse isn't just the plot of science fiction thrillers. Cosmology's flirting with the idea that our universe might be just one among many, each with its own story of formation, evolution, and perhaps even fate. What if these universes aren't just separate stories but interact? One of the most exciting speculations in cosmology is that if bubble universes exist, they might occasionally collide. Imagine soap bubbles expanding in a crowded sink. To approach each other, they eventually merge. Upon contact, they'll leave behind a scarred surface. Scientists have wondered, could our universe bear the marks of such meetings? In the vastness of space, nothing is impossible. In 2014, researchers studying the cosmic microwave background, or CMB, found a roundish pattern in the temperature variations of the early universe. Some suggested that this anomaly might be a collision scar, but it could also be just random noise. A later study confirmed this. But the idea of cosmic collisions persists. We can't directly observe the insides of these hypothetical colliding universes, so it's hard to test. And yet the idea continues to fascinate scientists. Other strange signals have been found in the CMB that could hint at other universes, such as cold spots, which appear to be abnormally cool regions. One proposed idea is that they come from light that has traveled to us from the neighboring universe. However, these observations are debated and might not stand up to closer scrutiny. Still, the mere suggestion of colliding universes keeps the question alive. No. 6. The fine-tuning problem. Our universe seems finely tuned for life. The forces of nature and the properties of matter are just right. Even tiny changes could make life impossible. Take gravity. If it were much weaker, galaxies wouldn't form, stars wouldn't shine, everything would fly apart. If gravity were slightly stronger, stars would burn too quickly, including our sun. Life as we know it would cease to exist. Then there's the cosmological constant, the energy density of empty space. It seems finely adjusted. If it were any bigger, galaxies couldn't form. The universe might have ripped itself apart long before we existed. There are about 25 physical constants in our universe, and all of them seem to be just right for life. How did they get that way? One answer is a designer. There's a guiding intelligence or law fine-tuning the universe for life. The other is the anthropic principle. This says that if there are countless universes, each with different physical constants, we should expect to find ourselves in one that supports life. Because if it didn't, we wouldn't be here to ask the question. While unsatisfying to some, the anthropic principle assumes that the multiverse exists. And that makes fine-tuning one of the main motivations for taking the multiverse seriously. No. 5. The measure problem. Infinity is a funny thing. It poses endless problems for the human mind, and scientists are no exception. In the context of the multiverse, infinity arises in a simple but troubling way. If the multiverse is infinite, then everything that can happen does happen. There are infinitely many copies of you in other universes. This creates what's called the measure problem. How can we assign probabilities to events in an infinite multiverse? If everything occurs infinitely often, how can we say one event is more likely than another? For example, suppose there's a universe where you won the lottery and another where you lost. Which is more likely? Since both outcomes occur infinitely often, both are equally likely. But that doesn't make sense. Probabilities should tell us something about likelihood, and yet in an infinite multiverse, everything is equally likely. Mathematicians are making progress on this problem, but it's one of the reasons why some physicists shy away from infinite multiverses. Without a proper understanding of probability, talking about what's likely or unlikely becomes meaningless. 4. Quantum branching, real or metaphor? Have you ever wondered if your decisions shape your reality? Quantum mechanics adds another layer to this age-old question. It suggests that every quantum event, every tiny decision, splits the universe into alternate realities. It's as though every time a quantum event occurs, the universe branches, creating parallel paths of infinite possibilities. Each split spawns a new version of our universe, where a different quantum choice was made. In this view, every possible outcome of a quantum event actually happens in some universe or worlds. This gives rise to a vast, tangled tree of realities, an infinite multiverse. But are these worlds physically real, or just a mathematical abstraction? Do they explain all quantum phenomena? The answer isn't straightforward, because most experiments in quantum mechanics don't require invoking multiple universes. It can be explained by more conventional interpretations. Nevertheless, the idea of quantum branching captures the imagination and remains a fascinating frontier in the exploration of reality. 3. Dark flow and cosmic anomalies. Have you heard of dark flow? It's a strange phenomenon that puzzled cosmologists when it was discovered in 2008. Large galaxy clusters seem to be streaming in one direction. This effect could be interpreted as evidence of another universe pulling on our own. However, when researchers checked again in 2015, the effect had vanished. While this original hypothesis was disproven, it's led to further investigations into the nature of our universe. Could there be other signs pointing to the existence of other universes? This question fuels the hunt for anomalies in the cosmic microwave background, the afterglow of the Big Bang. Any deviation from the expected could be a clue to other universes. And while no conclusive evidence has been found yet, the search continues. Remember the cold spots we talked about earlier? They're part of this investigation. Though initially flagged as potential signs of other universes, they now seem more likely to be quirks in data processing. But scientists are looking for other clues too. Some anomalies in the CMB have sparked debate. Some say they're imprints of collisions with other universes. Others argue that they're better explained by statistical fluctuations. Until we gather more data, it's hard to reach a verdict. But the hunt goes on. 2. Is the multiverse testable? There's a question that looms large over the multiverse, one that cuts to the heart of what science is about. Is the multiverse testable? This question challenges the very foundations of how we understand the universe. The essence of science lies in testing hypotheses, making predictions, and then seeing whether those predictions hold up. So the question is, can we devise tests for the multiverse? Proponents of the multiverse argue that, while we can't directly observe other universes, we can look for indirect evidence. For example, one prediction of eternal inflation is a stochastic gravitational wave background. That's a sort of noise in the fabric of space-time caused by quantum fluctuations. If detected, this could lend support to the idea of eternal inflation. But it's tough to pin down. There are other potential tests, too. Anomalies in the cosmic microwave background or unusual gravitational effects could potentially be explained by other universes. But the challenge is clear. Every potential piece of evidence is fraught with complexity. The difficulty is so great that some argue the multiverse isn't a scientific hypothesis at all. They say it's a metaphysical idea, a philosophical stance. According to this view, we can't falsify the multiverse, so it shouldn't be considered a scientific theory. 1. The frontier of possibility. What do you think? Is the multiverse just a scientist's wild imagination run amok, or is it a glimpse into a deeper truth? As we wrap up this journey through the labyrinth of the multiverse, let's take a moment to reflect on the bigger picture. If the multiverse exists, the implications are staggering. Universes with no stars or galaxies, universes with different laws of physics, universes where time flows backward or not at all. The possibilities are as limitless as the imagination itself. But perhaps the most unsettling thought is that somewhere out there, another version of you might be exploring these very ideas. What do you think? Would you like to know more about the multiverse? Does it excite you or confuse you? Let us know in the comments below. And while you're there, don't forget to hit the subscribe button to stay updated with our latest videos. The multiverse remains one of the most baffling and exciting frontiers of modern science. It challenges our understanding of reality, forcing us to confront the boundaries of knowledge. Whether the multiverse exists or not, the journey of exploring this idea pushes the limits of our imagination and understanding. As we continue to probe the depths of the cosmos, who knows what wonders and mysteries we might uncover next? When Galileo pointed his telescope toward the heavens in the early 17th century, he likely didn't know that he was chipping away at the foundations of human understanding. He became the first to witness the phases of Venus, substantiating Copernicus's heliocentric model of the solar system. But this revelation shook more than astronomy. It toppled a worldview that had held since antiquity, that Earth was the center of creation. Fast forward to today, and humanity stands poised on the brink of a new paradigm shift. The idea that our universe, with its galaxies, stars, and planets, might be just one bubble in an infinite expanse of reality. This radical notion isn't confined to science fiction. It's emerging as a serious area of scientific inquiry, challenging our understanding of existence itself. Before delving into these mind-bending concepts, let's first look at how we arrived at this cosmic crossroads. The seeds of the multiverse were sown by the giants of science. Albert Einstein, the architect of general relativity, laid the groundwork for our understanding of gravity, space, and time. His equations revealed that the fabric of the universe could warp and curve, giving rise to phenomena like black holes and gravitational waves. Enter Max Planck, the father of quantum theory, who revolutionized our understanding of the subatomic world. He proposed that energy, like light, comes in discrete packets called quanta. These two pillars of modern physics, general relativity and quantum mechanics, together offer a profound understanding of the universe. But they also pose a deep philosophical problem. General relativity describes the universe on a grand scale, where gravity reigns supreme, while quantum mechanics governs the subatomic realm where particles exhibit wave-like properties. Bridging these two domains has proven to be a major challenge. Enter string theory, one of the leading candidates for a unified theory. Proponents of string theory hypothesize that the fundamental constituents of the universe are tiny vibrating strings. The different vibrations of these strings give rise to all the particles and forces of nature. But to make this theory work, it requires a minimum of 6 spatial dimensions, in addition to the 3 we experience. What happened to the extra dimensions? According to string theory, they curled up into extremely small sizes, forming compact spaces. Here's where the multiverse comes into play. These curled-up dimensions could potentially create separate, self-contained universes. The idea is that there could be other regions of space that are physically disconnected from ours. Different sets of these compactified dimensions could lead to universes with different physical laws or constants. So one universe might have different forces or particles, while another could operate on completely different physical principles. This opens up the possibility of an infinite number of universes, each with its own set of physical rules. But this isn't just a theoretical exercise. String theory has practical implications too. It has led to significant advancements in mathematics, particularly in the areas of geometry and topology. Moreover, string theorists often use mathematical tools and insights from condensed matter physics, which has led to progress in that field as well. This cross-pollination of ideas has enriched both string theory and other areas of physics. Pushing the boundaries of human knowledge, the implications of the multiverse extend far beyond the realm of physics. It challenges our philosophical understanding of existence and reality. Consider the question of human identity. If an infinite number of universes exist, each with its own set of physical laws and constants, does that mean there are infinite versions of you, each making different choices, living different lives? The idea of infinite parallel universes where alternate versions of ourselves make different decisions and live out alternative realities is intriguing and philosophically challenging. It raises questions about free will, determinism, and the nature of identity. If every possible decision and action is playing out in some other universe, what does that say about the universe we find ourselves in? Does it diminish the significance of our choices? Or does it highlight the uniqueness and preciousness of our individual experiences? Some theories, such as the many worlds interpretation of quantum mechanics, propose that all possible outcomes of quantum events actually occur in separate universes. This interpretation suggests that every time a quantum event occurs, such as the collapse of a wave function, the universe splits, creating new parallel universes in which all possible outcomes are realized. In this view, the observer essentially goes along with the universe splitting, continuing to exist in the version that realizes their particular outcome. These separate universes coexist, but are inaccessible to each other. The idea of a constantly splitting universe can be seen as a way to explain the apparent randomness of quantum events without requiring any external influences or the introduction of new variables. Each split creates a distinct and separate reality, ensuring that every conceivable outcome is actualized. This branching narrative raises fascinating questions about identity. If every decision, action, and even thought leads to a split in the universe, then there would be infinite versions of every individual scattered across these branching timelines. In some versions, choices are made differently, leading to drastically different outcomes and identities. This concept challenges conventional notions of selfhood. If you are defined by your choices and actions, then who are you in a universe where those things are different? Conversely, it also highlights the uniqueness of our individual experiences. Every moment, every interaction, every choice we make is a defining factor in shaping our identity. However, the idea of infinite parallel universes raises practical as well as philosophical challenges. Verifying the existence of other universes through observation or experimentation seems nearly impossible. This raises questions about the nature of scientific inquiry and the limits of human knowledge. Can we ever truly know whether these parallel universes exist, or are we forever barred from accessing them? This limitation challenges the objectivity of science and reminds us of the boundaries of our current understanding. Despite these challenges, the multiverse concept has had a profound impact on our understanding of the universe and our place within it. It has pushed the boundaries of scientific inquiry, forcing us to confront the deepest mysteries of existence, whether or not other universes exist. The very act of exploring these ideas has enriched our understanding of physics, mathematics, and the nature of reality. It has also challenged our philosophical perspectives, forcing us to re-examine our notions of identity, free will, and the limits of human knowledge. Now let us discuss the impact of the multiverse on our conception of life and the search for extraterrestrial intelligence. The multiverse concept broadens the perspective on life beyond our planet. Traditionally, the search for extraterrestrial intelligence, SETI, focuses on the universe we inhabit, scanning the skies for signs of distant civilizations. But if multiple universes exist, each with its own unique physical laws and conditions, then life could arise in myriad forms. It might exist in universes where the chemistry is different, where the laws of physics vary, or even in dimensions beyond our perception. This challenges our anthropocentric view of life, suggesting that it might be more common than we imagine. In our universe, life arose under a very specific set of conditions. On Earth, life emerged in a world where water exists in liquid form, where organic molecules can assemble into complex structures, and where the energy from the sun drives biological processes. However, if other universes exist with different conditions, then life could thrive in environments vastly different from Earth. Some scientists speculate that life could exist in forms we can't comprehend, based on chemistries beyond carbon or energy sources we haven't discovered. The idea that life could exist in universes with different conditions challenges our preconceived notions of what life should look like. It suggests that life might be more resilient and adaptable than we think, able to flourish in environments that seem inhospitable from our perspective. Furthermore, the multiverse concept raises profound questions about the nature of life itself. If life is a universal phenomenon occurring across multiple universes, then what distinguishes life on Earth from life elsewhere? Does life always follow similar patterns regardless of the environment, or does it take on vastly different forms? Exploring these questions helps us better understand the origins and nature of life, not just on Earth, but potentially throughout the cosmos. As we continue to explore the concept of the multiverse, it's important to remember that it's still largely a theoretical idea. There's currently no direct observational evidence to support the existence of other universes. However, the absence of evidence isn't evidence of absence. The multiverse concept remains a fascinating area of scientific inquiry, and future discoveries and theories might shed more light on its validity. Moreover, the multiverse concept has pushed the boundaries of scientific thought, leading to significant advancements in various fields of study. Whether or not other universes exist, the pursuit of this idea has led to new discoveries and insights that have broadened our understanding of the universe. In conclusion, the journey from Galileo's telescopic revelations to the modern multiverse concept reflects humanity's insatiable curiosity about the universe. We've come full circle from a time when Earth was thought to be the center of creation to an era when we ponder the possibility of infinite universes. This shift in perspective challenges our understanding of existence, reality, and the very nature of our being. While the multiverse remains largely theoretical, its influence on science, philosophy, and our understanding of the cosmos is profound. It's a testament to the boundless curiosity and intellectual prowess of the human spirit that we even ask such profound questions. And as long as we continue to explore these mysteries, we'll undoubtedly push the boundaries of human knowledge even further. The concept of a multiverse may seem like a modern idea, born in physics labs and cosmology conferences, but in reality, it is the culmination of humanity's centuries-long quest to understand the cosmos. Every step, from early astronomy to space-age telescopes, pushed us closer to asking the question, could there be more than one universe? 1. The shift from Earth-centered to cosmos-centered in the ancient world. The cosmos was thought to revolve around Earth. Aristotle and Ptolemy described a finite universe with crystal spheres enclosing the heavens. Humanity's place seemed central and secure. But in the 16th century, Nicolaus Copernicus shattered that worldview. His heliocentric model placed the sun, not Earth, at the center. Over time, Galileo's telescope, Kepler's laws, and Newton's physics expanded our perspective further. The shift was profound. Earth was no longer the center of reality. Instead, we were a planet among planets, orbiting an ordinary star. This was the first step toward imagining that maybe even our universe isn't unique. 2. The expanding universe's next leap came in the 20th century. In the 1920s, Edwin Hubble observed that galaxies were receding from us. Their light stretched into redshifts. The universe itself was expanding. This discovery, combined with Albert Einstein's general relativity, laid the foundation for the Big Bang theory. Suddenly, the cosmos wasn't static, and eternal. It had a beginning. The Big Bang opened the door to questions of origins. If our universe had a starting point, could others also? Could universes be born in similar cosmic events? 3. The cosmic microwave background. Echoes of the beginning, 1965. Physicists Arno Penzias and Robert Wilson detected a faint hiss of microwave radiation from every direction in the sky. This was the cosmic microwave background, CMB, the cooled afterglow of the Big Bang. The discovery confirmed that our universe had indeed begun in a hot, dense state. Later satellites, COBE, 1989, WMAP 2001, and Planck 2009, mapped the CMB with increasing precision. They revealed tiny fluctuations, just as inflation theory predicted. Each of these missions strengthened the case for inflation, and with it, the possibility of multiple universes born from eternal inflation. 4. The rise of inflation theory in 1981. Alan Guth introduced cosmic inflation as a solution to the puzzles of the Big Bang. Shortly after, physicists like Andre Linde refined the idea into eternal inflation aversion that naturally produces a multiverse. This wasn't speculation for its own sake. It was a direct attempt to explain real cosmological data. The multiverse slipped into the discussion not as philosophy, but as physics. 5. Quantum physics and Everett's bold proposition. While another frontier was being explored in the microscopic realm, quantum mechanics developed in the early 20th century by pioneers like Niels Bohr. Werner Heisenberg and Erwin Schrödinger revealed a world of probabilities where particles could exist in superpositions of states. In 1957, Hugh Everett III proposed the many worlds interpretation. Every quantum event branches into multiple realities. Though controversial, Everett's idea planted a seed that would later intertwine with cosmology's multiverse discussions. 6. The string theory landscape of the 1980s and 1990s. Physicists sought a theory of everything to unify gravity with quantum mechanics. String theory emerged as a candidate, describing particles as tiny vibrating strings. But string theory didn't give a single unique universe. Instead, it suggested an enormous landscape of possible universes, each with different laws of physics. This created a new scientific framework where the multiverse wasn't an oddity, but a natural consequence. 7. Observations, anomalies, and ongoing debates. As telescopes improved, scientists began searching for signs of other universes. CMB anomalies like the cold spot were studied as possible bubble collision evidence. Large-scale motions of galaxies, so-called dark flow, sparked speculation about unseen influences beyond our observable universe. Particle accelerators like the Large Hadron Collider LHC probed high-energy physics. looking for hints of extra dimensions or new physics that could support multiverse ideas. Each experiment added data, sharpening the line between speculation and evidence. 8. The current frontier today, the multiverse, sits at the edge of science. Major physicists like Stephen Hawking, Leonard Susskind, Andre Linde, and Max Tegmark have all contributed to the debate, some arguing that the multiverse is a natural outcome of our best theories, others warning that it risks straying from testable science. The journey's ongoing. Every new telescope like the James Webb Space Telescope, every cosmic survey, and every particle physics experiment brings us closer to answers. 9. A story of human curiosity. The scientific journey to the multiverse is not just about equations or data. It's the story of human beings pushing against the limits of understanding. From Galileo's telescope to the Planck satellite, from Schrödinger's thought experiments to modern supercomputers, every step has been driven by the same impulse: to see beyond the horizon. And now, at the start of the 21st century, that horizon may include not just galaxies and stars, but countless universes. But where does this leave us? The scientific journey shows how we arrived here, but the road forward is even more fascinating. The final question remains: what does the future hold for the multiverse idea, and what ultimate questions does it raise about our place in reality? As the scientific exploration of the multiverse continues, there are several key points to consider about the future of this intriguing concept. First, the search for evidence. Scientists will continue to probe both theoretical predictions and real-world observations in pursuit of the multiverse. This includes analyzing data from particle accelerators, telescopes, and gravitational wave detectors for any hints of phenomena that can only be explained by the multiverse. Theoretical physicists will also continue to develop new models and refine existing ones, seeking those that make testable predictions. Second, technological advancements play a crucial role. Multiverse research relies on pushing the boundaries of technology. This means developing new and more powerful telescopes to observe the cosmos, building larger and more sophisticated particle accelerators to probe the fundamental constituents of matter, and creating advanced computer simulations to model complex multiverse scenarios. Each technological leap brings us closer to the ability to detect or rule out the multiverse. Third, interdisciplinary collaboration will be essential. Unlocking the secrets of the multiverse requires expertise from various fields. Physicists, astronomers, computer scientists, and mathematicians must work together to analyze data, develop models, and interpret results. This interdisciplinary approach fosters innovation and can lead to breakthroughs that might not have been possible within a single discipline. Fourth, public engagement and understanding are vital. The concept of the multiverse often captures the public imagination, but it also raises philosophical questions about the nature of reality. As scientists delve deeper into this topic, engaging the public through education and outreach will be crucial. This helps not only in conveying the excitement of these discoveries, but also in addressing the broader implications of living in a potentially multiverse. Fifth, ethical considerations will arise. If evidence for the multiverse is found, it may challenge our current understanding of the laws of nature and the origins of the universe. Scientists must be prepared to address the ethical questions that arise from such discoveries, such as the potential impact on religious beliefs and the societal implications of a radically transformed view of reality. Sixth, funding and support. Advancing multiverse research requires significant funding and support from governments and private institutions. As the scientific community embraces the multiverse as a legitimate area of inquiry, securing the necessary resources will be crucial for driving progress and ensuring that research remains at the forefront of scientific exploration. Finally, the future of multiverse research lies in maintaining a balance between openness to new ideas and rigorous scientific scrutiny. While the multiverse concept has its critics, it is essential to allow scientists the freedom to explore all potential explanations for the universe. At the same time, the scientific community must uphold rigorous standards of evidence and peer review to ensure that multiverse research does not stray into unfounded speculation. As we stand on the threshold of the 21st century, the multiverse beckons us with tantalizing possibilities. The road ahead will be filled with challenges, but the rewards of discovery could reshape our understanding of reality. By embracing a spirit of open inquiry, technological advancement, and unwavering curiosity. Humanity is poised to unlock the secrets of the multiverse, and in doing so, discover our true place in the grand tapestry of existence. In an age when technology and scientific inquiry intertwine to solve mysteries of the cosmos, a new question arises. Will we ever find proof of the multiverse? What if the existence of multiple universes were proven? What kind of impact would this have on our world? Imagine a world where the boundaries of reality aren't as fixed as we believe, where the tapestry of existence stretches out not just in space, but across a multitude of universes, each with their own unique set of physical laws, constants, and histories. This concept, while seemingly belonging to the realm of science fiction, is actually a staple in various forms of physics. As incredible as it sounds, the notion of the multiverse isn't merely a fantastical idea. It's a potential explanation for some of the biggest mysteries in the universe, from the behavior of subatomic particles to the origin of the universe itself. But the path to confirming or refuting this theory is riddled with challenges. So let us embark on a journey to explore whether we'll ever be able to prove the existence of other universes. One of the most significant hurdles in proving the existence of other universes is the very nature of these hypothetical realms. Most, if not all, proposed multiverses are fundamentally outside our observable universe. This means direct observation, and therefore confirmation, is impossible according to our current understanding of physics. However, just because we cannot observe these universes directly does not necessarily mean we cannot infer their existence indirectly. For example, the cosmic microwave background, or CMB. This is the leftover radiation from the Big Bang that serves as a kind of baby picture of the universe. By studying the CMB, scientists can analyze the conditions just 400,000 years after the Big Bang, when the universe was a hot, dense soup of elementary particles. One intriguing aspect of the multiverse theory is that it proposes a period of rapid expansion known as inflation in the universe's first moments. Inflationary theory suggests that our universe, along with possibly others, expanded exponentially in a fraction of a second before it started expanding at the slower rates we observe today. It's theorized that the energy fluctuations during this inflationary period could leave a unique pattern in the CMB. While some researchers have reported tentative signals, none have been confirmed as definitive evidence of inflation. However, future satellite-based telescopes like LIGHTBIRD or the Nancy Grace Roman telescope will be equipped to measure these minute variations in the CMB with unprecedented accuracy. If they detect the telltale signs of inflation, it would lend credence to the multiverse theory. Similarly, large-scale galaxy surveys like the Dark Energy Survey and the upcoming Vera Rubin Observatory will map billions of galaxies. By analyzing the positions and movements of these galaxies, scientists can study the distribution of matter in the observable universe. Some multiverse models predict that the structures within the observable universe could be influenced by the gravitational pull of objects outside our view, creating anomalies that might be detectable through these surveys. Although incredibly challenging, the sheer scale and precision of these projects increase the likelihood of detecting such signatures. Gravitational waves are ripples in the fabric of space-time caused by the acceleration of massive objects. They were first detected in 2015, opening a new window into the universe. Gravitational waves can carry information about the extreme conditions and events that created them, such as the collision of black holes or neutron stars. While the current detectors like LIGO and Virgo are designed to detect gravitational waves originating within our own universe, future detectors could be built to sense signals coming from other universes. This might sound far-fetched, but it's not entirely impossible. For instance, gravitational waves produced during the inflationary period could stretch across the multiverse, carrying information about the conditions and perhaps even the structure of other universes. Advanced detectors sensitive enough to pick up these faint signals could provide invaluable insights into the nature and extent of the multiverse. While direct observations are the most compelling form of evidence, they aren't the only avenue we can pursue. The future may also lie in the intersection of mathematics and computation. Theoretical physicists continue to develop and refine existing models of the multiverse. One promising avenue is string theory and its various extensions, which propose a vast landscape of possible universes. Mathematicians are working to understand the consistency and testability of these models. They're searching for unique features or signatures that could distinguish the multiverse from other theories. Moreover, advancements in computing power are leading to more sophisticated simulations of the universe. Using supercomputers, scientists can simulate the evolution of the universe under various conditions and model the potential for the emergence of other universes. By running countless simulations and comparing the results to observations of our universe, they can test the validity and parameters of different multiverse models. As we peer deeper into the cosmos and refine our theoretical understanding, we may find that certain aspects of the multiverse begin to appear less speculative and more concrete. Despite the immense challenges, scientists continue to explore various approaches to unraveling the mysteries of the multiverse. While direct observation remains the holy grail of scientific discovery, other paths like theoretical breakthroughs and advanced computations also hold immense promise. The future of multiverse research lies in interdisciplinary collaboration. By integrating insights from cosmology, particle physics, mathematics, computer science, and other fields, we can approach this enigma from multiple angles. But even if we never manage to prove the existence of other universes, the quest itself will undoubtedly expand our understanding of the universe and our place within it. The multiverse, whether proven or not, will continue to shape our philosophical discourse. The anthropic principle, which states that the universe must be suitable for life, because otherwise life could unexist to observe the universe, will likely remain central to discussions about the fine-tuning of the universe for life. Moreover, the concept of human identity will be challenged as we grapple with the implications of potentially infinite versions of ourselves. Each universe could harbor countless iterations of humanity, each making different choices, living different lives. This raises profound questions about free will, determinism, and the nature of individuality. Furthermore, the multiverse challenges our understanding of the nature of science itself. Should science be confined to what we can observe and measure? Or should it also encompass realms that are currently beyond our detection? The question of whether science can or should address the multiverse remains a hotly debated topic in philosophy of science. As technology advances and our understanding of the universe deepens, the multiverse will continue to captivate the human imagination. The prospect of other universes, while tantalizing, presents formidable challenges. Confirming their existence requires pushing the boundaries of observation, theory, and technology. Yet the pursuit of this understanding drives innovation and expands our intellectual horizons. Whether or not we find evidence of other universes, the journey itself will undoubtedly lead to profound discoveries and insights into the nature of reality. In conclusion, the possibility of other universes has captured the human imagination and continues to be a focal point of scientific exploration. While proving the existence of other universes poses significant challenges, advancements in observation, mathematics, and computation offer promising avenues for discovery. Direct observation of phenomena like cosmic microwave background radiation, galaxy surveys, and gravitational waves can provide indirect evidence of other universes. Theoretical breakthroughs in string theory and cosmological simulations can shed light on the nature and properties of these hypothetical realms. By embracing interdisciplinary collaboration and continuing to refine our methods, we may one day unlock the secrets of the multiverse. Whether we find other universes or not, the quest itself will undoubtedly enrich our understanding of the universe and our place within it. The concept of the multiverse pushes the boundaries of human curiosity and our relentless pursuit of knowledge. What do you think? Can we ever prove the existence of other universes? Let us know your thoughts in the comments below. And don't forget to subscribe for more videos like this. Together, let's continue to explore the wonders of the multiverse. As we stand at the precipice of new discoveries, one thing becomes clear. The story of the universe is far from over. The multiverse may remain shrouded in mystery, but the journey to understand it drives us forward. From the depths of space to the frontiers of mathematics, we relentlessly seek answers. And in doing so, we discover not only about the universe, but also about ourselves. The quest to unravel the multiverse is a testament to the boundless curiosity and ingenuity of the human spirit. No matter what the future holds, one thing is certain: the story of our universe is one worth exploring.